On this page, we'll go over the matched hair hypothesis test that was on the previous quiz. We'll also use this as an opportunity to review the types of conclusions that can be drawn from experiments. So the scenario on the previous quiz was that an instructor at Los Medanos College conducted an experiment with her statistics class to study the effects of texting on concentration. She created two audio clips in which she read two different lists of words. The treatment required students to send a short text message to a friend while listening to one of the audio clips. In the control setting, students simply listened to one of the audio clips without texting. Everyone wore earphones and listened to an audio clip in the same order, but a coin flip determined who was and was not texting each time. After each listening session, students had 2 minutes to write down all the words they could remember. 23 students participated in this experiment. Other information we are given that the mean of the differences for students in the sample is negative 6.96, and the standard deviation is 3.88. Here are the distribution of word counts. So the word count for the treatment group, notice the treatment group are the ones that were texting. Of course, they're busy. They're not really paying attention to the audio clip. So their text, the number of words they got right is smaller. It's over to the right, the smaller X values. But the control group that were not texting, they were actually paying attention. All their number of words is larger. It's because nothing was, nothing was holding them back, I guess is what I'm trying to say. they were actually paying attention. But because those are kind of skewed, both of those, the word count for the treatment, the word count for the control group, they're kind of skewed, one skewed left, one skewed right. That's why, like on previous pages, we talk about using a difference between them. Now look at the difference graph. It's just taking the average word count for the control and the treatment and subtracting them. And we get this more of a normal distribution. That's why we kind of use that. So you can kind of see that. Let's see now. The hypotheses, what were they? If I define what my null and alternative hypotheses are, let's see, the null hypothesis is a claim of no difference or no treatment effect. So I'm assuming that if you're texting or not texting, that you pretty much have the same memory and you're remembering the same amount of things. So the difference in word count shouldn't be anything. There should be no difference. So we say that the difference is 0. Similarly, if the students overall do not perform differently in the control and treatment settings, the mean of their differences is 0. So that's why our null hypothesis is that mu equals 0. But the alternative hypothesis, we're assuming that the treatment group is not going to do as well as the control group. So because mu is the difference between the two, mu was the word count for the treatment group minus the word count for the control group. I'm thinking the treatment group is going to do worse. Their number of words is less than the number of words for control. So I'm subtracting a bigger number from a smaller number. I'm going to get a negative. That's why our alternative hypothesis is that mu, the differences are going to be less than 0. In other words, negative. So we'll check the conditions. First, is there a random process that allows probability computations? Yes, the treatment order is randomly determined. They said a coin flip tells us who's going to get what treatment. So we are willing to proceed with the t-test. Next, we consider whether conditions are met for use of a t-model. The sample size is only 23, but the distribution of differences in the sample is not heavily skewed and does not contain outliers, like we kind of mentioned when we looked at the graphs above. So we assume that these differences are normally distributed in general when comparing these two treatments. We use the t-test with caution and plan to include a disclaimer in the results because the sample size is 23. That's not quite the cutoff that we wanted at 30. So we think we can use it. Basically, it looks like a normal distribution, but when we state our conclusion at the end, we should say something about, well, we might not be able to use a normal test, but we think we can. But here are some other observations that we'll make real quick here. If you're wondering why do we use only one of the 3 graphs of the data to check conditions, in this situation, the only distribution that is relevant to checking the guidelines for t-test is the distribution of differences. Why? Because this is a matched pair design. The hypotheses are about the effect of texting. So we take 2 measurements, with and without texting, and then subtract to look at the effect. Another question might be, does the experiment control confounding variables? Yeah, and anyway, back to that first one. I'm sorry, before I move on to the second question, we don't really care about how many words they got. Honestly, I don't care if you were texting, how many words did you count? And then if you were not texting, how many words did you count? I wanted to know if there was a difference. So that's why in this kind of particular this particular research problem, I don't care about how many words. Notice there's no numbers that talk about how many words anybody remembered. It was more just like, how many more does someone remember if they're not texting versus if they are? That's why we only look at differences, because that's really all we care about in this situation. But the next question was, does the experiment control confounding variables? The distribution of word counts for the treatment and control setting are skewed, but the distribution of differences is not. This is an illustration of how a matched pair design is in which treatment order is randomized can control the confounding effects of individual characteristics, such as natural ability and word puzzles. So because the same people were texting and trying to remember words, and the same people were not texting and trying to remember words, we're just comparing the same person, whether they were texting or not. So even though someone might be better at word puzzles or have a better memory, we're just measuring the differences. We're not comparing one person who has a good memory to someone who has a bad. We're just seeing if there's a change from when they text or when they're not. So for example, there was one student that was very good at recalling words. She recalled 12 words when texting and 18 when not texting. Her scores will definitely skew the mean of the treatment scores and skew the mean of the control scores, but her difference of -6, the 18 and the 12 subtracted, fits in with the differences of the other students. So let's calculate the test statistic. Now that we kind of feel like we can use t-scores here. The t-score is t equals -6.96. That was the mean difference divided by the standard deviation over the square root of the number of people. So it's mu over, well, I guess I should say the sample statistic. This should be, over the square root of n. So that's where we get -6.96 over s. The sample standard deviation was 3.88 over the square root of 23. If you put that in your calculator, -6.96 divided by 3.88, and then divide by square root of 23, should get about -8.60, or something, maybe with a few more digits, but if you round it, it should be good. And then remember, when you use the applet and your t-score, they want the degrees of freedom, and degrees of freedom should be n minus 1. In this case, n was the number of people in this study, 23 minus 1, so 22. If you use the applet, you put degrees of freedom as 22, and you put your t-score as -8.6, you should get that the area to the left of the t-value is 0, exactly 0, and the area to the right is exactly 1. So our conclusion is, since the p-value is essentially 0, we reject the null hypothesis, because that means that there's 0 probability that's going to happen. And even we've seen this before, that if the probability of anything is 0, that means it's impossible. There's no way it's going to happen. That means our null hypothesis must not have been right. Like the innocent until proven guilty thing that we talked about. If we're assuming that this person is innocent, but yet their testimony or something someone says along the way in the trial doesn't make sense, it's impossible, that must mean that our assumption of innocence must have been wrong. So same kind of thing here. The null hypothesis must be wrong because this is impossible. This situation, if I'm assuming the null hypothesis is true, I get some kind of contradiction. That means it can't be true. In context, the experiment provides strong enough evidence that texting weakens college students' concentration. The p-value is essentially 0. So those I say that so that those that kind of understand statistics will know, okay, well, how sure were you when you said you're going to reject the null hypothesis? I'm so sure that because the p-value was 0. I mean, it wasn't even just, oh, it's kind of close to 0. It was essentially 0 by 4 decimal points here. Students' ability to recall words was significantly worse when they were texting compared to their recall when they were not texting. But they put a disclaimer: the sample was too small to formally meet the requirements for a t-test. Based on the data, we're assuming that the differences in word recall would be normally distributed in general when comparing these two treatments in the population of all college students. The conclusion from this test is valid only if this assumption is true. So some important observations really quick here. Why did we include this disclaimer? Because it's good practice. Because if you don't include it, it seems like you checked all the requirements for a t-test and they passed and you are able to use a t-test. We didn't pass that test really, but we think that we can anyway. We're not really sure. So it's good to say that. Otherwise, people will assume that you've done something that you haven't, or this whole study design has passed a test that it has not. Also, can we use cause and effect language? We use cause and effect language here. Texting weakens concentration. It's valid because there's a random assignment of treatment order in the experiment. Recall that a coin flip determined the treatment order for each student. And I can't think of any confounding variables here. So I think it's okay to say that there is a cause and effect thing here. I don't think anything else could be causing the difference. They made sure that there was nothing else going on with these students. It shouldn't be, nothing else should be messing them up besides the texting. Also, can we generalize to all college students? In our conclusion, we also generalize to the population of college students total. Technically, this is acceptable only if the sample is a random sample from this population. Can we view the students in a statistics class as a random sample of college students for this experiment? That's debatable, but we think that this class is a representative sample of all college students when considering the effects of texting on concentration.